the architecture of the CPLDs. I hope this screen is visible to you. If not, just let me share it. Okay, is this visible, guys?
Yes, sir.
Okay, so last time we have seen, I just briefly go through whatever we have done last time. We have seen the architecture for CPLD Max 7000 series, a particular device, and we have also seen that there are a few building blocks which are common to each and every architecture, and that is the thing that you have to just keep in mind, that whatever may be the manufacturer, whosoever may be the manufacturer, the architecture always remains more or less similar. Okay, of course they will be calling those blocks separately, as you know, they coin their own names, they get the trademarks and patents and all those things, but ultimately the CPLD is composed of, as we have already seen, the logic array block, the programmable interconnect array, then the buried logic, IO control block. All these are the specific building blocks, typical building block, I'll say. So last time we have seen the architecture related to Max 7000 series. Today we will study the Xilinx device. Okay, so this is the architecture of the Xilinx device. Again, you can distinguish the typical blocks therein. That is the function blocks. Over in the previous architecture, it was called as the logic array block. Here it is called as a function block. Again, over there it was called as a PIA, programmable interconnect array. Here it is called as interconnect matrix. Then IO blocks we have as it is, and then we'll be having the other peripheral device circuits. Okay, so just have a look at this. So again, you'll see that the function blocks consist of, these are the basic building blocks which we roughly call as the macro cells. These are consisting of the AND plane, the OR plane, and some flip-flops, okay, which you can program the redirect the output of that particular logic block to via a particular flip-flop. So we call it as registered, otherwise we call it as direct output. So these are the available packages for the Xilinx CPLD, since this device is manufactured by Xilinx, which is the top most company as far as the manufacture of programmable devices is concerned. So there are various device names over here. You can see the table. All right. Now, do you see any peculiarity? Just try to find out the details over here like this, that for this XC9536, this 36 actually indicates the number of macro cells. So here for this particular device, there are 36 macro cells. On your application, you are supposed to select a particular device, number one. Okay, now you'll see that sorry, it is available in various different packages like 44-pin VQFP, PLCC, and so on and so forth, PQFP, TQFP, and all those things. Okay, now do you see one peculiarity here? That this 9572 is available in both 44-pin PLCC as well as 48-pin CSP as well as 84-pin PLCC. Okay, if you look at the lower version 9536, it is available. So you'll see that there is an overlap. It simply means that XC9536 is available in this 44-pin PLCC. 9572 is also available in the same package. Similarly, 9572 is available in 84-pin PLCC, as well as the next higher end is available. 95108 is available also in the same package. Do you see any logic behind it? It's more or less common sense. Why do we have such overlapping devices? Guys, please answer. Let it be wrong.
Because the architecture is more or less same.
No. Take a hypothetical example case where you start with 9536. Okay. And then you manufacture the PCB, all the peripherals, everything. So final PCB is ready. And maybe there is some change in the design which makes this particular device insufficient as far as macro cells are concerned. So you already have invested a lot in your PCB. Investing in PCB is not a joke, because ultimately you could require to have a lot of copies of that PCB, right? The number of units is more always. So you make such 100 such units, and then suddenly you say no, it's 9536 because of some modifications is insufficient. The number of macro cells is not sufficient enough for my design. In that case, what to do? Do I have to throw away all the PCBs? So Xilinx has given a very intelligent answer to this, and that is you can migrate to 9572 because the package is same, everything is same, and the only thing is that the number of macro cells is twice. So you can simply change your target device itself. This kind of some sort of what is called as backward compatibility is maintained between the two subsequent consecutive devices. Okay, so that you can always go for the higher version if required. Have you understood, guys?
Yes.
Please respond. Guys, please respond.
So this overlapping concept is I'm confused in this.
That's what I'm saying. See, if you are planning to design a particular product, and you started with the first device, that is 9536, and you said fine, my logic is not that much, so 36 macro cells will be sufficient for me. Okay, with that you go ahead and manufacture the PCBs, fabricate the PCBs, and suddenly maybe there is some kind of design requirement or some last minute changes which dictate that the number of macro cells is less. Okay, whereas you require more macro cells because of some additional functionality that you are introducing at the last minute. Okay, so if there is no pin compatible, there is no package compatible device available which is having higher macro cells, higher capacity, then you would have to throw away all your PCBs. But this particular scheme that is being used by Xilinx is such that you are saved from that problem. In the way, say for example, I'm migrating to the next higher version, that is 9572. I have twice the number of macro cells. Here it is 36, here it is 72. So I don't have to discard the PCBs. I can simply use the next target device and design my product. Is it clear now?
Yes, sir.
So this is the way in which these people, they intelligently float their products so that you are not stuck with any such problem. Okay? Of course, the cost of the device also goes on increasing as the number of macro cells increase. Okay, some new packages are introduced by Xilinx. For example, this is a VQFP, very fine pitch quad flat pack, or very thin quad flat package, as it is commonly known as. Okay, these are all SMD packages. Then there is something called as chip scale package. This is another interesting thing. okay, which they have introduced. Some heat sinked quad flat package. So here there is a heat sink at the bottom, as you can see here, so that the power dissipation does not increase the core temperature. There is something called as ball grid array. These are again, whenever the pin count is more, even your quad packages will be insufficient. In that case, the package that is preferred is the ball grid array. You can see that the number of pins is definitely more, and runs in hundreds and 200s also. Okay, now let us have a look at the device marking. Whenever you look at the CPLD, the device will have these markings. Okay, what are the markings? The logo of the company, then the company name, which is the manufacturer. This is the device type. So here you have XC95 series. So you have the XC95 series. X stands for Xilinx, C stands for CPLD. Okay, and this 95 is the series. And then you can have this XXX actually is the number of macro cells. So XC9536 means that it is having 36 macro cells with it. Okay, then the package is also printed on the device, and the speed grade, importantly. We have already spoken about what is called as a speed grade. So what is the speed grade? What do you mean by speed grade? Yes? Guys, what do you mean by speed grade? Am I audible? Students?
Yes, sir.
So answer.
Sir, color grading app.
It's not color grading. Speed grade.
It indicates time delay.
Yes, actually it indicates the maximum delay between any two pins, okay, of the device. So if one pin you are calling as input, other is calling as output, in that case, what is the maximum delay that will happen between these two pins? Okay, will be the speed grade. And obviously, the lower the speed grade, the better, the faster is the device, because this is in nanoseconds. So this is a 7 nanosecond speed grade device. If you have 5 nanosecond speed grade device, it is much more faster than this one. Remember that. C indicates the operating temperature range. Okay. So this is how the device marking is there. Then what are the features of this CPLD 95 series of CPLDs? High performance. You can have as low as 5 nanoseconds pin-to-pin logic delays. Okay. Then one of the feature is that it is in-system programmable. That also at 5 volts. And of course, the number of program erase cycles is also very important, because there is some degrading which happens with the flash memory. So in that case, 10,000 program erase cycles it supports. So 10,000 times you can just program it, erase it, and reprogram it. Then there is something called as pin locking. We'll see about that later on. Then you have what is called as a flexible 36V18 function block. So if you correlate this with your PLA, we also had this kind of, let us say, specification over there, which says 36V18 means what? Actually, there are 90 product terms which drive any or all of the 18 macro cells. So this 18 indicates macro cells. Okay. With function blocks, there are global and product term clocks. Output enables set reset signals. which is extensive IEEE standard 1149.1. There is something called as boundary scan, which is also called as Jtag support. Then you have slew rate control. We have already seen such kinds of things in the previous architecture. Then we have slew rate control on individual pins, user programmable ground pin capability, extended pattern security features for design protection. So there is a security feature also, though you cannot reverse engineer it. Okay. Then drive capacity is 24 milliamperes. All right. So what does it mean? It can source a maximum of 24 milliamperes. Okay, which is significant. Then it has got 3.3 volts or 5 volts input output capability. So CPLD XC series is comparatively old. So in those days, they used to have 5 volts as well as 3.3 volt logic. Advanced CMOS 5 volt flash technology, and it supports parallel programming. Now this is one interesting thing that you can get with Xilinx devices, that you can parallelly program multiple target devices. Okay, you need not do them individually, because that will take time. Say for example, if your product units, if you want to manufacture and if it runs in hundreds and thousands, so programming each and every device would be very, very time consuming. So instead of that, they use what is called as a multiple devices programming. Okay, this is the architecture for XC9500. You can see here the basic building blocks remain the same. So you have the function block. In function block, you have the macro cells, of course, AND plane, OR plane, and the macro cells. Okay, these are connected to what is called as the interconnect matrix, which they call as fast connect 2. Okay, so this is again a trademark name which has been which has been filed by Xilinx. They are calling their switch in a different way. I mean, maybe because they have some different architecture to support that. Okay, so each manufacturer will have his own architecture to do the same job. Okay, then you have the IO blocks and ultimately the IOs. The additional thing that you'll see here is the Jtag controller and the ISP controller. We have already seen last time. What do you mean by in-system programming? Okay, so this XC9500 architecture also supports in-system programming. In addition to that, it has got what is called as a Jtag controller. Jtag stands for Joint Test Action Group, and they have devised a protocol of some sort which you can use for testing, programming, and some other tasks also. Debugging mostly. So there are these three important pins there: clock, reset, tri-state pins. Pins labeled GCK, there are three of them: GSR 1, GTS 2 or 4, and can be used for special purposes, where GCK is the global clock, GSR is the global set reset, GTS is the global tri-state control. Okay. Let us have a deeper look at the individual blocks. We have the function blocks. As you can see, we have the programmable AND array. Then you have the product term allocators, and then the macro cell. Okay. This is what is the function comprises the function block. Then you have the interconnect. From this side, you can see there are interconnects. So technically, we can say that there are 36 inputs and 18 outputs. So that is the reason why we call it as 36V18 for this particular architecture. Okay. So you have global set reset, you have global clocks, all associated with this function block. The AND plane exists as shown by the crossing wires. This is what we were talking about, AND plane. It can accept inputs from IO blocks and other function blocks, or feedback from the same function block. Okay, the terms are then OR together using a fixed number of OR gates, and terms are selected via a large multiplexer. Outputs of this multiplexer can be sent straight out of the block or through a clock flip-flop. Again, whether you want a registered output or an unregistered one, you can choose that. Specifically, when we will be using or designing for the finite state machines, you would require a registered output. This particular block includes additional logic such as selectable XOR and a master reset signal. Okay, so these are the features of this function block. Each function block is comprised of 18 independent macro cells. We have already said that 36 inputs and 18 outputs per each function block. Remember that so many such function blocks are there inside the device, each capable of implementing a combinatorial or combinational. It is also called as combinatorial or combinational. Both the terminologies are valid. Or registered function, that is a flip-flop if you want. The function block also receives global clock, output enable, and set reset signals. It generates 18 outputs that drive what is called as the fast connect switch matrix. This fast connect is a trademarked name for the switch matrix that Xilinx has designed. So it's a switch matrix. These 18 outputs and their corresponding output enable signals also drive the input output block. Okay. Logic within this function block is implemented. Again, we already know how to implement it as the SOP, that is sum of products representation. 36 inputs provide 70 true and complement signals into the programmable AND array to form 90 product terms. So this is what the AND plane and the OR plane together along with macro cells will generate. Any number of these product terms up to 90 available can be allocated to each macro cell by what is called as a product term allocator. Let us have a deeper look at the macro cell itself. You'll see the typical blocks over here, just like Max 7000 series. Okay, just forget about this for the time being. Just see that the output of the product term, that is, you can have the AND plane and then this is the OR. So this is the product term. Output over here is a product term and that is given to XOR. It can directly be given as the output or it can go via the flip-flop to get the registered output. Okay, so this is the macro cell which is used by Xilinx XC9500 series. Okay, we have already seen this XOR. We've already seen how an XOR can be used as a programmable ground, or it can also, that is, or you can have inversion, logic inversion. So that logic inversion is decided by this particular multiplexer. Similarly, whether registered output is required or not is decided by this flip-flop via this control. Okay, this control, in fact, clock. It's a clock, and then this is set. Sorry, this is the product term set. So set control and reset control. So this particular multiplexer M3 will decide whether the output is direct or whether it is via the flip-flop. This one. Okay. Let us have a look at the macro cell clock and set reset capability. As you can see here, that it has got a global set reset, global clock. All these pins are available so that you can have a master set reset or a master clock, which is also called as a global clock here. And there is something called as product term allocator. So if I want to route the output, these things automatically using Xilinx software itself. Okay, so you don't have to bother about it. So just have a look at the architecture, in what way these people have implemented that particular architecture. This is the I/O block. Now you see, this is actually the actual interface to the pin, that is I/O. So what are the various important things that you observe from here is that you have a user programmable ground, you have a pull-up resistor. So this pull-up resistor can be enabled if I enable this block. Okay, there is a slew rate control, there is an input buffer if you want to use this as an input pin. Okay, and what are these two diodes for? Can anyone tell me? Yes, basic devices. Why are those diodes used over there? Yes, please answer. Guys,
Voltage divider.
no, how can it be a voltage divider? Come on, those are diodes, not resistors. Anyone? Please think about it. These are called as the clamp diodes. These are meant for the protection of the pin. That is, if some voltage crosses above a certain value, one of the diodes will get forward biased and clamp it to that value. Are you getting this? Suppose by any chance, because of an inductive load or something like that, it is quite possible that this voltage, it may get exposed to a higher voltage. So if this is, let us say, configured at 5 volts, anything more than 5 will damage the circuitry. So if more than 5 volts, say 6 volts or 7 volts appear over here, what will happen? Look at the way in which it's connected. If 7 volts appear here, what will happen? Yes? D1 will get forward biased. D1 will get forward biased. Are you able to understand this? Guys?
Yes, sir.
So if D1 gets forward biased, what is the voltage across the diode? What is the voltage across a forward bias silicon junction diode?
0.7.
Yes?
0.7.
0.7 volts. So here you have 7 volts. Here you are internally, maybe it is 5 volts. So what will be the voltage at this point? At the input to your input buffer, what will be the voltage? Yes? Here you have 5 volts. Here you have 5. Yes, so what is the voltage at this point?
Sir, what is the input voltage?
This voltage, I am superimposing a voltage equal to 7 volts, for example, 7.
Okay, sir.
VCCINT is, let us say, 5 volts. So what will be the maximum voltage? What will be the voltage at this point, at the anode of this D1? Cathode is at 5 volts, anode is at 7 volts.
2 volts. Cathode is -2.
No. How can it be -2? What is the voltage drop across diode? Forward bias diode?
1.3 volts.
0.7 volts.
So it will.
So it will be this volts, this voltage plus 0.7. So it will not be more than 5.7 volts. Are you able to understand this? Basic.
Yes, sir.
So no matter you apply 10 volts here, what will still be the voltage? What will be the voltage? If you apply, instead of 7 now apply 10 volts. Still this will be 5.7. Are you able to understand this? Guys?
Yes, sir.
Sure. This is the basic protection
Yes.
mechanism which you will find in most of the motor drivers, so that it gets protected from over voltage situation. What about this lower diode? Why is it there? We have understood the functioning of D1. What about D2? Yes? Tell me. Come on, guys. Can you answer the question, students, please? Or you don't know?
If 7 volts come across the cathode of D2, so it will get reverse biased.
No. What is the require? I mean, why do you want
Requirement.
D2? My question is not. I have not told you as what is the voltage that is being applied here. I have told you. I mean, I am asking you what is the
Yeah.
function of this diode D2? We have understood the function of D1, but what about D2?
Like it's connected like how we connect Zener, so something of that sort.
Yes. Yes, you are on the right track.
Okay. So to
For example, if there is a negative voltage somehow,
okay.
if there is a negative 5 volts here, by mistake somebody has connected negative 5 volts, what will be the voltage over here?
Negative 5 volts. So
What? How come? See, I am applying minus 5 volts here, so it will be coming over here. So the voltage across diode D2 will be 1. No, anode will be at 0 volts and cathode will be at minus 5 volts. So what will be the voltage at cathode? Are you able to understand the question? These are very, very basic things. What will happen if there is minus 5 volts here and anode of the diode D2 is at ground? Obviously, this will be at a higher potential. This diode will start conducting. D2 will start conducting and it will clamp this voltage to minus 0.7 volts. So even if you apply negative 5 volts here, the diode will make sure that this point is clamped to a voltage negative. Guys, have you understood? Please respond. Guys, please respond. Am I audible?
sir, I think there was some call drop in between.
Yes, there was a call drop, but have you understood the concept? Why D2, D1 and D2, what are their functions? Have you understood? Tell me, yes or no?
Yes, sir. It's
Sure. So it will
yes.
protect the input buffer from dangerous voltages. Okay, this is the protection mechanism, D1 and D2. Other things like slew control we have already seen. User programmable ground also we have seen, but it is in a different context. But at the same time, you can have a different ground value here. Okay. So all these can be configured. Then the pull-up resistor. Many times you require the a pull-up resistor. So there is an internal pull-up resistor which can be enabled. Let us have a look at the switch matrix itself. So the switch matrix is simply the collection of all the cross points which manifest in the form of your as the transistors as switches. So every cross point is a switch over there, and you simply have to program those. Okay. What is the job of the switch matrix is to connect the input pins to the macro cell inputs to the function block, and then finally the macro cell output to the output pins. And of course, internal connection is also possible. So that is the job of your switch matrix. Okay, that was as far as XC9500 series was concerned. Now we have another advanced CPLD from Xilinx called as Cool Runner 2. Of course, this also is now pretty old, but then you'll see that there are enhancements in this particular architecture. What are the features? It is optimized for 1.8 volt systems. Remember, I told you that there are various different core logic values, voltages available. We have 5 volts, we started with 5 volts, then we have 3.3, then we have 1.8, and slowly down to 1.5 and even 1.2 also. Okay, so many of your core logic microcontroller cores work on 1.2 volt logic. What do you mean by 1.2 volt logic? What do I mean by core voltage? Can anyone tell me? We have already discussed this earlier. What do you mean by core voltage? Yes? What do you mean by core voltage? And why we are going down? That is why are we downscaling the voltage? Again, this is sort of if you recollect this concept, do you recollect this concept? Guys, you are supposed to answer questions. What do you mean by core voltage?
So the voltage which is across the chip means the core part of the chip.
It simply means that your internal logic works on this voltage.
Yes, sir.
Internal logic. Okay. So your VCC can be 5 volts, VCC can be 3.3, and so on and so forth. Okay. So it is optimized for this 1.8 volts core logic systems. So it is a low power CPLD. Densities range from 32 to 512 macro cells. It is based on 0.18 micron, that is 180 nanometer CMOS technology, which has got an optimized architecture, okay, with multi-voltage I/O operation. That is, it can interface with any logic which is 1.5 volt to 3.3 volts. Remember, now they have dropped this 5 volts because by that time all the sophisticated state-of-the-art systems were coming with controllers were coming with 3.3 volt core logic. It has got advanced system features like fast in-system programming, on-the-fly reconfiguration, BST, that is boundary scan technique test. Then you have multiple I/O banks, low power management, and so on and so forth. And there are some external signal control, flexible clocking modes are there. We have got internal clock dividers as divide by 2, 4, right up to divide by 16. Then global signal options with macro cell control, global multiple clocks, phase selection you can have. So you can select the phases also of the clock. Okay, many times you require a biphasic system. Okay, so there you can have the facility. Then you have got multiple global output enables, global set reset. It has again got advanced design security, and of course the open drain output option, so that you can have wired OR, okay, and LED drive. Then you have the optional bus hold 3-state or weak pull up on select IO pins, optional configuration grounds on unused IO pins, mixed IO voltages compatible with 1.4 volts right up to 3.3 volts as a core logic. Wide package available. It's available in wide number of packages, including what is called as a chip scale package, BGA, fine line BGA, TQFP, and so on and so forth. Okay. Again, it is also guaranteed to give you support 1000 program erase cycles. Okay. The data that is there is guaranteed to have a retention time of 20 years. This is the device part name. So it is XC2C. So C, the second C stands for the Cool Runner family. Okay. Again, the same kind of nomenclature. This is the architecture. Now you can again distinguish. You can identify the common blocks. You have the programmable logic array, and you have the micro cell MC1 through MC16. So 16 macro cells. Okay, with different for different outputs, so 16 outputs, and then you have this AIM is nothing but the interconnect matrix. Okay, then you have the IO blocks, and of course there are various different things like boundary scan and in-circuit in-system programmability over there. So this is the function block of the Cool Runner 2 family. So you have PLA, macro cells. This is going to be common everywhere. Okay, nothing more here. Then you have something called as macro cells in this, which is a far more advanced version. You have different modes. Okay, so you can have a flip-flop, a common normal flip-flop, conventional flip-flop, or you can use it as a latch, or you can use it as a dual edge clock also, a clocked flip-flop also. Okay, so more enhanced functionality is provided here. Other things are more or less same. What are the new controls which are seen here? Like CT control terms are available to be shared for key functions within the function block and are generally used whenever the exact same logic function would be repeatedly created. So this actually is a simple way of replicating the logic, of telling the CPLD that the logic has been replicated. The control term, product term, CT product terms are available for function block clocking, CTC, asynchronous set, reset, and output enable. Now here they are calling, instead of PIA or instead of calling it as some other guys, am I audible?
Yes, sir.
Okay. So the AIM is directed by the software to deliver up to a set of 40 signals to each function block for the creation of logic. Results from all these function block macro cells as well as all pin inputs can circulate back through the AIM for additional connections to all the other function blocks. Okay, that also obviously has to be possible. AIM minimizes both propagation delay and power as it makes attachments to the various function blocks. So they have concentrated in this design on the betterment of the interconnect matrix, because this is the major place where a lot of switching will take place, and so it has to be it has to have a minimum propagation delay and also less power consumption. These are the IO blocks Again, you can go through this architecture here. So you can see the common things that we have already seen. Okay. Again, interesting thing is that the output pins are grouped in large banks, which allow interfacing with different logic levels, different core voltage levels. Now, a very simple example which I would quote is why would we require these multiple logic levels, multiple core voltages? Yes. Suppose you want to write an interface between the USB of a computer, a personal computer or laptop, whatever, conventional computer, that is to say. And if you want to interface it with some device which runs on 3.3 volts logic. So you can very well make use of such CPLDs for that. In fact, most of the devices, they do have this capability, this feature. Yeah, for example, your simple pen drive which you normally use. What is a pen drive consisting of, guys? Do you know what is pen drive made up of? Use that, no? Every now and then. Your pen drive, flash drive also it is called as. So what is it made up of? Guys? Come on guys, answer the question. Do you have any idea? What is this? Guys, please respond.
Like it's memory, so like
it's only a memory, but what type of memory? What type of memory do you have? It's a flash device. So flash memory, obviously, right?
yes.
And only flash memory.
It's also like wrong.
It must be having a microcontroller which does the job of addressing this memory, fetching the data or writing the data, right? Now this microcontroller may be, for the reasons known only to the designers, may have 3.3 volt logic, but it has to speak to your PC, which has a core voltage, which has got a peripheral voltage of 5 volts. All the USB drives will have 5 volt capability, isn't it? So how to interface this 3.3 volt logic to 5 volts? So CPLDs play a very important role there. So you can use this device whenever such multi-voltage interfacing is required. Okay, this is, they are calling it as a data gate. Okay. Again, the construction is very similar to what we have already seen. So what is this data gate? It is used for power reduction. Each IO pin has a series switch that can block the arrival of free running signals that are not of interest. Signals that serve no use may increase power consumption, and therefore they can be disabled. Of course, users are free to choose their own design and selection and sections to participate in the data gate function. Data gate is a logic function that drives what is called as an assertion rail threaded to the medium and the high density CPLDs, the code runner 2 devices. Designer can select inputs to be blocked under the control of data gate function. So this is one additional function that they have introduced, which enables or disables the access to this switching signals. Output signals that do not switch are held by the bus hold feature. Any set of input pins can be chosen to participate in the data gate function. So please remember that there are some added circuitry. There is some added circuitry which enables us to more efficiently make use of the device in a more efficient way. Then lastly, how do you select or how do you finalize your target device, specifically when it is related to when you are supposed to select it as a CPLD device. So when considering a CPLD for use, the following issues should be taken into account. Number one, the programming technology. We have already seen quite a lot about programming technology. We have seen the comparative features of these technologies. So whether it is EPROM based, E2PROM based or flash EPROM, this will determine the equipment that may be needed to program the device and whether they can be programmed only once or multiple times. So this is a very important consideration, the programming technology. Second specification will be the function block capability. How many function blocks are there in the device? How many product and sum terms can be used? What are the maximum and minimum and maximum delays through the logic? What additional resources are there? Are there any RAM blocks, or are there any XOR, XNOR, ALUs, etc.? What kind of register controls are available, like the global set, reset, clock? How many are local inputs to the function block and how many are global chip-wide inputs? This also is important. Many times you run out of IOs, general purpose IOs. What kind of clock drivers are there in the device, and what is the worst case skew of the clock signal on the chip? This will actually help determine the maximum frequency at which you can run the device. IO capability, how many IOs are independent, used for any function, and how many are dedicated for clock or in clock input or for master reset or for anything else? What is the output drive capability in terms of voltage levels and currents? And what kind of logic is included in IO block that can be used to increase the functionality of the design? So all these three are very important, let us say, criteria for selection of CPLDs. I want all of you to just write this down. All this, whatever is visible on the screen, because question may be asked as to on what basis will you select a CPLD. Okay. Just tell me once you complete writing this down. Okay, have you finished? Guys?
So, one more minute, please.
Hello.
Yes. Have you finished?
Yes, sir.
All right. So with that, we finish with the CPLD, and we will start with the FPGA. Okay. Just hold on while I change the slides.
Sir, we cannot see the screen.
Yeah, I'm just changing the slide now.
Okay, okay.
I'm changing the presentation itself, so please hold on. Okay. Is this presentation visible to all? FPGA part 1?
Yes, sir.
Yes, sir.
Okay. Okay. So there are some key terms that we must study before we study the architecture of the FPGA. Basically, FPGA stands for Field Programmable Gate Array. Now, its architecture is totally different if you compare it with the CPLD. It is absolutely different. So this is another solution for your target device. So there, what are the key terms? The key terms are like lookup table, LUT. So this is a integral. This is an integral component of any FPGA. It is a circuit that implements a combinational logic function by storing a list of output variables that will correspond to all possible input combinations. In simple plain words, it is a truth table. All right. Then what is a CLB? It's a configurable logic block, and it is the programmable logic block used in FPGA. There is something called as logic element. It is a circuit internal to FPGA used to implement a logic function as a lookup table. Then you have something called as cascade chain, a circuit in the FPGA that allows the input width of a Boolean function to expand beyond the width of one logic element. Okay, so with that you can expand the width of the Boolean function. Carry chain, a circuit in FPGA that is optimized for efficient operation of carry functions between logic elements. There is a separate provision for the carry signals. Okay, they need not go through the switching matrix or whatever. Then there is something called as DCM, Digital Clock Manager. It is a very important circuit which will offer various clock management functions. Clock trees, distribution of the clock lines along the FPGA architecture. Okay. So FPGA, field programmable gate arrays. The structure is much like a gate array ASIC. Now, if you recollect that we had discussed something about the classification of these devices. One was the ASIC. Everything is ASIC in general term. In specific term, ASIC is one which is application specific integrated circuit and which you design in various different ways right from the silicon itself. Okay. Again, that in ASIC, if you remember the tree, you had something called as a full custom design, then you had the gate array design and so on and so forth. So this particular term has been borrowed from that particular let us say type of circuit which is called as a gate array. Now what basically is a gate array? You can visualize it as islands of programmable logic. Of course, when we talk about gate arrays from ASIC point of view, they are different. Again, of course, they are arrays of gates. So many different gates are there, and then we have a structure which can be replicated. So this is the basic building block in the ASIC gate array design. Okay, a similar kind of concept is borrowed in field programmable gate arrays, and that is the reason why it is called as field programmable and gate arrays, of course. So what we have here is as islands of programmable logic in a sea of programmable interconnect, and that is what makes it different than the CPLD. It is more closer to programmable ASIC. So you can also say that, as I said, ASIC, it has got gate array design. This is very similar to that. Of course, the only thing is that this is programmable, whereas ASIC, once you design it, you cannot reprogram. It can be scaled to larger sizes. Large emphasis is laid on interconnect routing. This is the most, let us say, vulnerable part of the FPGA. Vulnerable in the sense, critical part. Why? Because if the interconnection is routed in a haphazard way, the delays will be more. Delays associated will be more. And so you have to be very critical about this. Timing performance, therefore, is difficult to predict. As I said, you cannot, there are a large number of interconnection routings being done, and that is the reason why, as in CPLD, you cannot predict the timing performance of the FPGA very easily. Let us have a look at the generic FPGA architecture. FPGA will contain these blocks. What are the blocks? And resistors. It may have embedded microprocessors and microcontrollers or microcontrollers, and it has got high-speed serial transceivers. So these are some advancements and some differences as far as the CPLD and the FPGA architecture are concerned. Architectures are concerned. This is a FPGA architecture. As you can see, again the basic building blocks are programmable blocks, but they are arranged in a particular way. This blue or gray, grayish area that you see is all interconnect. So we have a large number of interconnects. Okay, and that is the reason why it is called as the sea of, rather islands of programmable logic floating in the sea of interconnects. That is what it is popularly termed as. Okay, then you have these IO blocks which also are programmable. All right. So this is basically the architecture generic architecture of FPGA. Are you able to understand this, guys?
Yes.
Yes, sir.
Okay. Okay. Now, many times this FPGA is described in terms of fabric. Okay, which means actually the underlying structure of the device. So it is quite possible that some FPGAs may be these programmable logic blocks may be laid out in a different way, or maybe small number in large quantity or large number in small quantity. So that actually describes what is called as the fabric of the FPGA. Please remember that. Okay. So how are FPGAs programmed? You can use the SRAM, you can use anti-fuse, you can use flash or hybrid flash SRAM. This is the FPGA fabric. So it's a repetitive structure, as you can see, of programmable logic block, and each of them is connected to every other block by means of these interconnects. Switch matrices again, which are the programmable interconnects. All right. And that brings us to the types of architecture. As I said, the fabric is described in terms of whether it is fine grained or it is coarse grained. These are two distinct areas, two distinct words which are used for describing the fabric. What do you mean by fine grained? Each programmable logic block can be used to implement only a very simple function. In fine grained architecture, this is going to be the scenario. For example, it might be possible to configure the block to act as any 3-input function, such as primitive logic gate and or NAND, etc., or a storage element, that is a latch or a flip-flop. Okay, these types of architectures are said to be particularly efficient when executing the systolic algorithm, that is the functions that benefit from massively parallel implementations. So again, depending on your design, you have to select whether to go for fine-grained architecture or for coarse-grained architecture for the FPGA. Fine-grained implementations require a relatively large number of connections into and out of each block compared to the amount of functionality that can be supported by those blocks. As I said, the function blocks carry out very simple tasks, very small tasks, so as to say, but the number of such programmable logic blocks will be more, and so it is called as fine grained. All right. But at the same time, it has got its own weaknesses, like large number of blocks will indicate large number of programmable interconnects also. Okay. So you have large number of connections here. What about coarse grained? So in case of coarse-grained architecture, each logic block will contain relatively large amount of logic compared to their fine-grained counterparts. For example, logic block might contain four input LUTs, lookup tables, 4 multiplexer, 4 D-type flip-flops, and some fast carry logic. So here you have a bigger function block. So in the given area, there will be few number of function blocks, but each of them will be able to carry out let us say a more amount of logic design. As the granularity of the block increases to medium grained and high, the amount of connectors or connections into the block decreases, obviously, compared to the amount of functionality that they can support. As we have already seen, in case of fine grained, you require a large number of connections. If you go towards the coarse grained, the number of connections required will be fewer. Of course, not very few, but it will be definitely less than the fine-grained architecture. Then there are various logic realization techniques. How exactly the logic is realized? In case of CPLD, it is straightforward. You have the and the or planes. You have the sum of the product implementation. But in FPGAs, the way in which the logic is implemented is different. There are two fundamental methods. One is the multiplexer based method, and the other one is the lookup table based method. Let us see. So in multiplexer based method, this is based on one simple and very important theorem that you must have studied in your digital circuits, and that is called as the Shannon's decomposition theorem. Have you heard about this, guys?
No, sir.
No, you have not studied this theorem?
Not in digital. I mean, Shannon's decomposition theorem we haven't.
You haven't studied. Okay, so here it is. Let fx be a switching function on n variables. Then what you can do is you can factor it out. That fa can be factored. So I can take out a, which is the input, one of the inputs of this n variables. So when a is one of the variables, and you can take out a common. I mean, in the sense you can build this kind of factoring such that it is ai into f into, in the sense, this is into in the sense what ended with. So a ended with f1 or with inverted version of a1 ai, that is ai bar ended with f2. So you can break this function into two sub functions. So this fx can be broken down into f1x and f2x, and you can take out one particular input which is common to both of them in this way. Okay, so this is a ended with f1 or with a bar ended with f2, or you can put it this way, f, which is a function of n variables. Now if I want to eliminate one particular variable, I'll break it down into two functions using this particular theorem called as Shannon's decomposition theorem. So in this case, I can have the function which is in terms of a fewer variables. It is now n minus 1 because a I am taking out of this function. Similarly, this function is different, but it is taking, again we are taking out a out of it. So basically what is happening is I am eliminating the input variable and simplifying these things. This is an example multiplexer implementation using the theorem that we have already seen. So consider a 3-input function. All right. So the function is y is a ANDed with b ORed with c. Of course, you know how this works. Precedence and all that. All right. So this function can now be broken down into two sub-functions y1 and y2. And I want to eliminate a. I want to eliminate a. How will I do that? You make a partition like this. This is a truth table. A, B, C are the inputs. Y is the output. Now I'll break this down into two partitions. One where all the inputs of A is 0 and the one where all the inputs of A is 1. So now I can ignore, for these functions, sub-functions, I can ignore the value of A because I know always A is always going to be 0. Here I know always the A is going to be 1. So I can create sub-functions like this. Okay, just a part of this truth table. This is the truth table. But now the complexity has reduced. Why? Because I have eliminated one input variable itself. So this is less complex. So I can write this y1, this part as y1, and this y is c itself. I mean, this is how you write the Boolean expressions, right? So y1 is nothing but c. You can see here, when c is 1, y is also 1, irrespective of what is the value of b. So y is simply equal to c. What is the second function? See here, look at the second function. This looks like the truth table of which gate? Truth table of
OR gate.
OR gate, correct. So it is nothing but b ORed with c. So the second function is y2, which is b ORed with c. Simple. So now I can write the entire function, the complete the function y in terms of y1 and y2 and a bar and a like this. Are you able to understand this?
Yes, sir.
So I can write y as a bar ANDed with c, that is y1, and a ANDed with y2, that is b or c. Try to understand this concept. Very, very important. Okay. Have you understood this part?
Yeah, yes, sir.
Okay. Now I can eliminate b further, where I can make b partition over here like this for b equal to zeros and b equal to ones here, and then I can simply write y as a function y3 and y4 as functions of only one variable. So y2 is nothing but y3 ANDed with y4, which is, so what is y2? It is b bar ANDed with c or with b ANDed with 1. Similar way, I'm using the same kind of technique and decomposing the functions one by one. This is how you can implement using a multiplexer. So you have this as y1, this as y2, and you can implement it with a multiplexer like this. So these are the basic components, 2 components basically, and we are using it to get the complete implementation using the multiplexer. Okay? Yes, this is another possible implementation. So there are various ways in which you can implement. If you don't remember how to implement functions using multiplexers, Boolean functions using multiplexers, please revise that part. All right. Then we'll see another implementation methodology or mechanism, and that is the lookup table based. So an n input lookup table is that it can implement any possible n input combinational circuit. Underlying concept is relatively very simple. Group of input signals is used as index or pointer to a lookup table. The contents of this table are arranged such that the cell pointed to by each input combination contains the desired value. This is the LUT implementation. See if you understand this architecture. So you have these inputs as A, B, and C, and these cells will decide the output for various combinations of A, B, and C. So this is using what is called as the pass transistors. In simple plain way, simple transistors which we use as switches. So if I want to program a functionality, what is my job? I don't have to do anything except for just filling in these values corresponding to the output that you want. I'll just fill up these values. That's all. And this is nothing but the truth table. The output. I hope it is one and the same here. It may not be the same, but doesn't matter. It is the same 0 1 0 1 0 triple 1. Okay, so what you have to do is only fill up these SRAM cells with the output, that is Y, from the truth table, and use this structure. I want all of you to find out how this works. Okay, how is the logic implemented? Just for kind of homework. You can tell me next time whenever I ask you. how does it function properly. Okay? Another implementation can be with the help of a transmission gate. I hope all of you know what is a transmission gate. Do you know what is a transmission gate? Guys? Yes or no?
Yes, sir. Heard about it, but not able to recollect.
Not able to recollect. Okay, it is an anti-parallel connection of NMOS and PMOS devices. Okay. So depending on the gate values, the value is either value from the drain is passed to the gate or it is blocked. In very simple plain words. If you look at the transmission gate CMOS, the symbol is there in front of you. But if you look at the CMOS backend, you'll be able to understand it's working very easily. We cannot go into that CMOS. I do have that, but let me see if I can find it somewhere. Just hold on for some time. Okay, let me hit. All right, is it visible now? Okay, is it visible?
Yes, yes, sir, it's visible.
This is a transmission gate. In to out. Hello? Hello, guys?
Yes, sir.
There was a call drop, I guess. Okay, so look at the truth table. When A is high, obviously A bar will be low. Okay. In that case, if in is high, then out is also high. So this value of in is passed on to the output. Similarly, if A is high and if in is low, then the same value is passed on to the output. So it actually behaves like a gate. All right. It is called as a transmission gate. A switch in simple plain words. The disadvantage of using a single transistor is there. A lot of disadvantages are there. Basically, the pass transistor will have either the weak outputs and that is the reason why we use this transmission gate, which employs the CMOS, that is complementary MOS transistors. Yeah. Just like the CMOS inverter. So if you see, the CMOS inverter has got PMOS as well as NMOS, and it is the basic, the very first gate that you can design is the inverting gate using two transistors, one PMOS and another NMOS. Similarly, this is again a very important basic building block in CMOS technology, which is called as a transmission gate. Okay, and this is also built using two transistors, complementary transistors, PMOS and NMOS. All right. Okay. Then the number of LUTs, that is the lookup tables. It has been statistically concluded. Now this is important, that a 4-input LUT is more than sufficient for many devices. You will ask me the question, okay, what about 5 input, 6 input? But of course, you can increase the width of your Boolean equation by extending with the other neighboring LUTs. Okay, but generally speaking, 4 input LUTs is more than sufficient according to statistics. One additional advantage of LUT based programming block is that the SRAM cells which are forming the LUTs, as you can see here, we have SRAM cells here. Okay, so what you have to do is only program these, that's all, and your logic function is can be implemented. So those cells, they can double up as a small block of RAM also. So it is going to be a 16:1 RAM. If you don't use that LUT for implementing a logic function, you can use those cells as a block of RAM. That is one very, very important advantage of the LUT based FPGAs. This is called as a distributed RAM. So you can just have these memory locations and you can use them. Also, all SRAM cells are effectively connected in a chain. This is so as to facilitate the programming. But this is also giving a very important, say for example, all these SRAM cells in neighboring LUTs, they are all connected in a chain. Okay, so this is one chain, I mean this is one block, the next block will also follow, but they are connected in form of what is called as a shift resistor. So the value will shift, you can shift the values as a big huge shift resistor all around the FPGA. That is also very important functionality, because your testing and verification can be very easily done. We'll see, if time permits, we'll see the testability also, but then I don't know whether we are having that in the syllabus or not. Now, because of these advantages, majority of the today's FPGA architectures are LUT based. Remember this. The major FPGA vendors then were Xilinx was there, Altera, Atmel, Lattice, and so on and so forth. Okay, they used SRAM based FPGA. Now they have shifted over to the flash type. Okay, then you have antifuse also, based on antifuse technology also that is available. So this is the very first Xilinx device called Xilinx series. The older families are XC3000, XC4000, and XC5200. Okay. Okay. As you can see here that these old families are already outdated, but unfortunately our syllabus still mentions some of them. Anyways, but they were based on what is called as 0.5 micrometer technology, 0.35 micrometer and 0.25 micrometer technology. These are absolutely not recommended for modern designs. Then there are two basic criteria families. One is called as a low cost family, and the other is called as a high performance family for as far as the Xilinx device FPGAs are concerned. In low cost family, you have the Spartan series, Spartan 2, Spartan 2E, and Spartan 3. I think in your lab you will be having access to Spartan 3. I don't remember exactly, but we do have Spartan 3 board. You can confirm this with your practical coordinator. Then we have high performance families also. They are called as Vertex. Vertex E, Vertex 2, Vertex 2 Pro, Vertex 4 and Vertex 5. So I think they have gone up to Vertex 8, I guess now. Again, Vertex has got different flavors depending on what exactly do you want to design. For example, LX stands for logic only, LXT stands for logic and some serial communication if you want. SXT, whether you want DSP functions, and then FXT, whether you'll be having the embedded. I mean, if you want to write some kind of a IP core for a microcontroller, that also can be done. But for that, you may require the FXT series. These are the Xilinx devices. I know this is slightly outdated, but see how the Xilinx devices progressed in terms of the number of gates. Latest was 2012-13, Vertex 5, 24 million gates. Now again, FPGAs are talked of in terms of the number of gates. Okay, which gates? The NAND gates specifically. Why? Because the NAND gates are universal gates. So we have, let us say, the power of an FPGA, how much it can accommodate, how much logic it can implement, depends on the number of gates. So it started with XC2000 with, let us say, only 1000 gates, and look at this particular Vertex 5, which has got 24 million gates. Okay, so this is how they went for advancements in the FPGAs. Before we go into the FPGAs, I think I will stop here for today. Is that fine with all of you?
Yes, sir.
Okay. Then I'll stop the recording. Tomorrow we will continue with the FPGA devices. All right.
Okay, sir.